Hello everyone. This next video is going to be a little bit of a kind of a mixture of a couple different things, but there's one hiccup that multiple people have run into that I wanted to clarify. Some of you have been attempting to start simulations just by going to where the file is saved and trying to open it directly from here. This usually doesn't work because it uses the wrong settings when it tries to open the file. It uses the default settings. So just like when you try and open a file, double clicking on it like you would like a Word or an Excel file generally doesn't work. What you should do instead is go open the software itself. Give this a second to come up. And within the software, do file load or the little folder icon to load a file. This will give you the exact same menu as if you were creating a new file. The only difference is, let me set this up just so. The only difference is you tell it which file do you want to load. In this case, I told it where the file is, and I asked it for some properties about the file. This should open the file just fine. If you can create a new file successfully, you can load a file in this way. And you should load a file every time in this way. This makes sure it's using the right number of cores, it's using the right licensing scheme, and basically gives you a chance to verify that it should indeed be working. It might seem like double clicking would work better, and in some very limited cases that are not applicable to us, it might. But in general, just open the software and load the file from within the software. Okay, so that was kind of minor point number one. The major thing that I wanted to talk about is actually I might need to find a slightly different file. Hold on just a second here. Let me load. I'm going to load up the conical one. And this will be proof that you can have two simulations running at once. Notice it actually gave me a little bit of an interesting error here. It says that, well, it's a little bit complicated phraseology, but contention on 14 processes could not be resolved. CPU affinity will be cleared. What happened is I opened one simulation and told it use 14 threads. Then I went and opened another simulation and also told it to use 14 threads. That's a problem because suddenly if I try and run both of these simulations at once, it's going to run out of cores. It's not going to have enough processor threads to run both of these. So it's going to start time sharing them, which is very inefficient. Because it takes extra work to, so to speak, pick up the simulation, do some work on it, put it down, pick up the other one, do some work on it, put it down, pick up the other one, rinse, repeat. So you can open multiple simulations at once, but never run multiple simulations at once unless the total number of cores you assign to all of them is less than or equal to the physical core count of your computer. That's a bit of an aside. That's really not what I was after. What I was after was looking at our kind of sort of our simulation. We used a flat outlet, I believe, for pretty much everything we did, but basically the same type of configuration as you have for assignment one. And I want to emphasize a point here. This is a two-dimensional simulation. But lots of things need areas. Lots of things need distances. So how does that work? I mean, we modeled this. Let me new scene, empty. Hold on, let me show how we modeled this. New display or surface. There we go. We modeled this like this, where it's cylinders, a conical cylinder, or a cylindrical cone-ish, another cylinder, and a sphere. So what we did is we cut this in half. So let me show that really fast here. Oh, did that not work? 2D domain. There, we cut this in half, right? So the question, some of you ran into this, is what are we simulating here? You might think, oh, we're simulating a cylinder. We're not, actually. Like, the software knows that this is the shape that it had originally, but what it's simulating is entirely just this flat surface right here. And when it does a two-dimensional simulation, it doesn't treat it like it's a cylinder. It doesn't treat it like it's a revolution or a body of revolution. It treats it as if it's an extrusion. What do I mean by that? If we look at this, it's not that there's a circle here at the inlet and we just can't see it because we're looking at an edge on. It's not that there's, this dome at the outlet. No. It is simulating as if it is exactly this cross section, and this extends 1 meter directly into the page and stops. So what this is simulating, and let me draft this really quickly here. I hadn't actually planned on this, so I'm going to be doing this live, so to speak. This won't be perfectly accurate, but it's going to be close enough where you can get the idea of what's going on here. Oh, actually, this probably would work pretty darn well. Let's see. Theoretically, this should be a closed form. Can I extrude it? I can. Now this is going to be, well, that's perfect. It's as if we're simulating something that looks like this. This is the outlet, this is the inlet, and the rest of these are walls. This is effectively what we're simulating, except it assumed this was 0.1 meters. It treats the depth into and out of the page as 1 meter. So a really long aspect ratio rectangular nozzle, except it doesn't take into account any of the three-dimensional effects. So every slice of this nozzle looks the exact same. So we don't bother simulating all of them. We just simulate one of them. The very slice on the very end. Now this isn't obviously quite our nozzle. I didn't make this quite symmetric, but you get the idea. So we are not simulating something that looks more like this. We are indeed simulating something that looks at least vaguely like this in a more physical reality. Our domain is still the exact same, this cross section on the end, but we're simulating it in 2 dimensions built from a cylinder. So you have to kind of get your brain away from thinking of this as a cylinder because it's not. Some people I saw using pi r squared to calculate areas. That is not correct for this application. There is a different application that is related where that is absolutely what happens, but this is not that. So that is kind of point 2 here. Point 3 is, or kind of the major point for today is, let's look at, how did I set up these boundary conditions? It looks like I'm trying to heat a wall. Give me just a sec here. Make sure that I'm not heat. Oh yeah, this one says it's a heat source. So let me turn that off. Thermal specification, adiabatic. I think I also turned this into an inlet, which we do not want. This is a pressure outlet all of a sudden. This is a velocity inlet. I'm going to give it 20 meters per second. So I'm going to make this very similar to what we have for... Oh, I did turn this into air. Okay, this is no longer water. This is air. Let's just verify that really quickly here. It says this gas is air. Perfect. That should be fine. Really don't need gravity, but yeah, we really don't need gravity, so I'm going to turn gravity off. We're running left, right, more or less parallel to gravity, I think, or along iso lines of gravity. So let's see here. That should be fine. Let's see here. What else? I think that should be okay. So I'm going to clear this and hit run. And let's just set up some reports really quickly here. So we're going to look at, we're actually going to look at force, because this is something that we can verify with momentum calculations. If we look at the walls, so pretty much anything that's not the inlet or the outlet, wait a second, hold on. Something's wrong here. Where are my regions? Why do I have 2? Oh, there's a very, very tiny sliver here. This needs to be a pressure outlet. Let's try that again. Clear solution, clear, run. Theoretically, this should run somewhat better. And let's just go ahead and make sure that none of the rest of these have thermal conditions applied to them. Okay, they don't. Okay, let's plot something else. Let's plot static pressures. Static pressure. There we go. So we can look at momentum by, or we can check what are the forces on these walls, because you have different pressures, right? You're going to get some amount of pressure force that's pushing this thing that way. So you might have to assume that the outside pressure is the same everywhere. But you can use momentum to figure out, okay, how much force is this thing actually receiving. Let's see here. On all of these exterior walls. It's down here. So not the inlet or the outlet, but everything else. So it thinks 53 newtons, 53.5 newtons. In the X direction. Let's look at let's see here, the surface average, total pressure, at the outlet. We're going to look at all of our outlet surfaces here. So P underscore T out. We're going to just copy this, paste that, rename. We're going to also make another one for the inlet. So the only thing I'm doing is I'm just changing what I'm making a couple of different of these reports, and pressure. That really doesn't have dynamic pressure. Oh, well, we can figure out dynamic pressure by actually sort of looking at our own Okay, I'm going to do a slightly more advanced thing. Don't worry too much about following along yet, but if you want to, feel free to follow along. And that is, we're going to create our own field function. So we are going to create a scalar field function. So this is down in Tools under Field Functions. We're going to create a new scalar field function. We're going to create a field function for dynamic pressure. It is going to, well, when you create a field function, you get to name it. So we're going to call this dynamic pressure. It is a scalar quantity. It has dimensions of what? It's probably going to have dimensions of pressure, right? So we just put a 1 here, so that says it has units of pressure. How is it defined? Well, we get this handy dandy menu, we get to define it. Okay. So let's scroll down here to, we should have total pressure somewhere. Perfect. Total pressure minus static pressure. Done. And we can then go back to our reports. I'm going to select both of them and say we are looking at dynamic pressure. Boom. Now we're going to go ahead and just plot all of these real fast. We're going to create and monitor and report on a single plot. Q in, Q out, create, monitor, and plot from report. P in, P out, create, monitor, and plot from report. We are going to create, monitor, and plot for that. And one more thing, we're going to look at the mass flow rate. So this is going to be m dot in, m dot in, paste, m dot out. The only difference is we change the outlet one to our outlets. I'm going to take both of these, create monitor and plot from report. We have a whole bunch of plots, not particularly usefully named because they're multiple plots. So m dot port 3 is static pressure. Report 2, I think, is I don't know what it is. Let's look. Dynamic pressure. Port 1 is total pressure. And we can create a new monitor plot. And let's just add all of the pressures to a new plot. We can look at them all in one place. All pressure. Okay, hit run. And even better yet, this runs fast enough. We're going to clear the solution just so we can see how these change from the beginning. Oh yeah, this converter is real fast, doesn't it? It's not quite not changing at all, but it's mostly not changing. Let's see here. Dynamic pressure, total pressure. Let's see here. Residuals. Okay, residuals are now flatlining. This is pretty much considered converged at this point, I would think. M dot. Where's our... Oh, that's our force right here. Yeah, this is pretty much rock solidly converged. Scroll way the hell to the bottom here. Okay, so back to our scenes. That's a little bit of an aside. That's not what I wanted to look at. What I did want to look at is one thing, whereas we could also look at pressure coefficients. Now, let's look at a plot of pressure coefficient and see what's up here. Because we talked about... Actually, let me start here. We talked about if we want to do, let's say, a... oh, what am I looking for? Oh, yeah, if we want to do a force coefficient, we have these reference values, right? Reference density, reference velocity, reference area. We need to update these so they make sense. That's fine. We do need to update them if we do a report, but this is not the only thing that has those reference values. So let's say we want to look at how coefficient of pressure changes through this nozzle. Let's see here. I think it's actually called pressure coefficient because of sorting reasons. Pressure coefficient right there. And it says the pressure coefficient is between negative about 600 up to about 1600. Okay, that doesn't seem right. Something's very wrong here. Why? Well, what goes into pressure coefficient? You have the static pressure, which it knows, but you also have free stream static pressure. You also have free stream dynamic pressure. How does it know what those are? It doesn't. Just like your coefficient of lift, it has no idea what your free stream density, free stream velocity, and free stream static pressure are. It has no idea. None. We need to define those. Where do we define those? So this is actually down in tools under field functions. Most of these do not have things that you change. If we look down here in this little properties box, I'm going to just hit the down arrow a whole bunch, and you see that most of these are grayed out. They don't have anything we can change. Some of them, oh hey look, boundary sliver cell indicator has a tolerance value. We can adjust this. Do we want the tolerance to be higher or lower? We could change that value. Keep on going. Chevron quality, same thing. We could give it an angle and we can give it some tolerances. Edge length, we can whether it uses average, minimum, maximum, etc. Effective conductivity, viscosity. Let's see here. But the one we're interested in, and there are several others like this, is pressure coefficient right here. Oh, hey, this has a whole bunch of values we can change. We can tell it what reference density we want. Ah, that changed these values, right? It changed this from 1 to 1.18. It's negative 500 instead of like negative 600, and 1300 instead of 1600. Reference pressure, 0 is probably fine. Reference velocity, though, I think we use 30 meters a second, I want to say. Let me double check that. Velocity, oh, we use 20 meters a second. That would explain why that's wrong. At least in part. Let's see here. So notice that it still doesn't think it's coming in at a coefficient of pressure of 1. Why is that? Let me, where did my pressure coefficient go? Reference pressure. So part of this, I think, is that if we go and plot static pressure for a second here, it's coming in at like, I don't know, 600 pascals. Right, this is our inlet, right? It's coming in at like 600 pascals. We can actually find an exact value because we plotted this. Pressure coefficient. So let's go look for our static pressure plot. And hey, at the inlet, it thinks it's 743.75. So let's go here and put in 743.75. And I bet you if we go back and plot or look at our scene for coefficient of pressure, well, it's basically 0 here and just drops. The static pressure keeps on dropping as it accelerates. You get a small pressure rise here due to this corner. Get a pressure drop at this corner, but largely it starts at a coefficient of pressure of 0, which you'll recall is free stream velocity by most definitions. And then it drops throughout the entire thing as the flow accelerates. There's one other thing here. Where's total pressure? The only other thing we notice here is we see the total pressure in and the total pressure out are slightly different, actually. It's dropped by about 100 pascals. Now, you might think that, oh, hey, wait a second. Total pressure is supposed to be constant. But total pressure is only supposed to be constant in the case where energy is conserved. In this case, it's actually not. Right? The flow is generating forces through viscosity. dissipating energy into the walls kinematically. Not thermally, but kinematically. And we're losing some energy in the flow. So we get a drop in total pressure through this thing. Now, that's all well and good. The big point here is that there are some things, especially things with the word coefficient in them, where if you plot them, you might get gibberish values until you come down here and change some of the parameters that govern. I just copied that by accident. And change some of the parameters that govern how they're calculated, like the heat transfer coefficient. You need to tell it what the reference temperature is. If your free stream isn't at 300 Kelvin, this is going to be horrendously wrong. Let me see here. Where is another good one? The Nusselt number. This is related to thermal conductivity and stuff like that. It's a thermofluid number, reference number, similar to Reynolds number, but for the thermodynamic aspects. You need to change the reference temperature, change the reference length, change the reference thermal conductivity if necessary to get reasonable numbers for these sort of dimensionless coefficients. Do they have one for Reynolds number, incidentally? Doesn't particularly look like it. You can make your own if you wanted to, but again, some of these, especially things that are supposed to be dimensionless, not just include the word coefficient, but things that are supposed to be dimensionless, those can have values that you need to tweak down here under field functions. If you're not dealing with that, don't worry about it too much. But it can potentially matter if you're doing things like trying to look at pressure coefficient. Because if you do that and don't change these, your values are probably gibberish. Now, if we want to measure values at the inlet, we want to measure values at the outlet. If we want to measure values along the walls, that's fine. But how the bloody hell do we measure if we want to know, like, the pressure here? Right here. Or right here. Or right here. Well, you need somewhere to measure the pressure is kind of the problem. You need a surface that defines where you want to make the measurement. We don't have a surface where we want the measurement. You're like, okay, well, we could break this into more parts. You could have 2 cylinders, and that kind of works, but also kind of really doesn't. You can also do derived parts. This is a new folder we haven't discussed yet. You can do a lot of different things with derived parts. What I would like to discuss today are primarily probes and sections. So, what we're going to look at first is sections. If we want to measure the pressure, let's say immediately at this line right here, right where this nozzle constriction starts and right where this nozzle constriction ends. We can do that if we create a section plane right here and right here. So section plane, if you, well, let me back up a second. If you go to derived parts, new part, section plane, if you have a geometry scene open, you'll get this handy dandy little GUI that lets you mess with things. And you can type in the numbers or you can drag this around and see where it goes, right? In this case, we want one at 0, 0, 0 because that's the start of this constriction. Generally, I hit no displayer unless you very specifically want to see the section plane you just made. I will leave it. I will have it make a new surface displayer for the moment. You make sure, the plane is defined by an origin and a line that is normal to the plane. So you define the origin, in this case 0, 0, 0, and the normal is x, positive x. So the plane is oriented vertically. We're looking at it edge on, pointed to the right. You could create multiples where you could say, hey, I want to create 2 sections, one here and 1 meter downstream. I could say I want to create 3 sections between 0 and 1 meters down, 10 sections, so you'd have one at like 0, 0, or 0, 0 0.1, 0 0.2, etc. You could say I want 5 sections that start at 0 and they have 1 meter in between them. Or you could say that I just want a plane at 0. I want a plane at 0 0.15, 0 0.25, 0 0.5, 1.325, 1.31, etc. Right? You could just plug in whatever the hell you want. In this case, we only want one plane. We want one plane here, which we can measure separately, and one plane here, which we can measure separately. If we create a whole bunch of planes, they're probably not measurable separately. Well, actually, tell you what, let's go ahead and 0.15, I think. We'll go ahead and create this. And if we close this, we can see that it has a single plane right there. And it doesn't seem to really have another one. Oh, 0. There we go. 0 space 0.15, we can see we have a second plane right here. So if we put 0.3, we get one right there. The problem is these are both part of the same thing. If we ask it to measure the m dot through, let's say, this plane, we're probably going to get double the value that we should. Okay, look. The mass flow rate through this plane section is pretty much exactly twice what it is through the inlet because it's measuring it here, it's measuring it here, and then it's adding them together. The mass flow rate through the plane is like 9.5 when it's like 4.75 through the inlet. So we could create multiple planes all at once, but we really don't want to do that because we want to measure quantities separately here and here. So I'm going to go ahead and remove this section plane. So all I did is I just unchecked derived parts. So put that back the way it was. So we have one section plane. So I'm going to call this, let's see here, constriction start. I'm going to create a copy and constriction end. Let's see here. And we want this one to occur at the end of the constriction, which is 0.3 meters from the origin. So we have a plane there and there. And we can measure quantities at these two locations. So let's say we want to measure what is the static pressure at these 2 points. So if we want to measure the pressure at the constriction inlet, we can tell it, hey, let's measure not anything on the region level. Let's measure on this derived part, the section plane at the constriction beginning. Constriction out. Menu down. Same thing, except we select the constriction end. So we're told that the static pressure at the outlet of this thing is a little bit over 735. Oh, sorry, at the beginning is a little bit over 735 pascals, and at the end is only about 12 pascals. Which makes sense, because most of our pressure change is happening here, between those two planes. We could also measure this in the middle. And create another kind of arbitrary plane. Let's see here. In the middle, and say, what is the static pressure right about here? So right about in the middle of this thing, we are about 550 pascals. Hasn't dropped all the way yet. I've only dropped about a third of the way, honestly. But this is one way that we can measure pressures at different points where we don't have surfaces. We can also use other things. We can use other types of sections in very similar ways. We could use a cylindrical section, which doesn't make a huge amount of sense for this. Let's see here. If we make a cylinder with a radius of 1 inch, no displayer. Oh, you have to select the input part, by the way. When you're selecting a derived part, you have to select the input part. It selected the right one by default before, but definitely you must select the right input part here. Let's see here. Did this cylindrical section work? Yep. Created a cylinder right here. Now, this is in 2D, so the cylinder is oriented normal to the screen. We could have also made a sphere. We could have also done a lot of things. But we could make a measurement through this cylinder just like we would anything else. If we make a measurement of m dots through this, what do you think we're going to get? What's the total mass flow through that cylinder? Well, probably nothing, because on one side it's entering, on the other side it's leaving. So, oh, hey, look, we're talking less than a tenth of well, we're talking on the order of, it thinks the difference is a couple of tenths of a gram per second. And remember, the mass flow through this entire thing is on the order of single-digit kilograms per second. So that's just effectively rounding error. We're talking a couple of tenths of a gram per second. So the mass flow rate through our little cylindrical section is effectively 0. I'm just setting this report back to the way it was, by the way. So bear with me just a second. There we go. So we have, they all work in basically the same way. A constrained plane is a little bit weird. Don't worry about that one too much for the moment. That's a little bit more advanced. But we could also make a measurement point. Let's say we don't want to know what the pressure is necessarily over a surface. We want to know what it is at a location. Okay, let's create a point probe. Let's move this. Really, 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 really close. Right there. Let's put a point probe right there. No displayer. Create. Could also move it down here. Really, 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 really close to this corner. Create. We have a pair of points. One there, one there. So let's say I want to know. I'm only going to make one report for the purposes of demonstrating, but because this is a point, you really can't do averages. You have to do like a maximum or a minimum, which really isn't the maximum or minimum. It's just whatever the hell the value of this is at the point. So I'm going to select static pressure real fast here. And I'm going to ask it for the value on just one of the, well, actually, tell you what, I'm going to select both of these points. We asked for the maximum pressure, so I'm going to select both of these points. And it's going to tell us the maximum pressure. What do we think that is? It's probably going to be about 850, 900 pascals, give or take. Oh, I overshot it a little bit. I said 850. It's 780. But it's definitely over here. This is the higher pressure. We asked for the minimum. Let's see here, new report, user minimum. Static pressure. And we ask for it on our 2 points. Well, the minimum is clearly over here on the right. Static pressure in this little corner is actually about negative almost 300 pascals. It's a very small area, but right there it is that low. What time is it? Okay. Let's see here. What else? Now, when you're asking for the maximum and minimum, you can do this funny thing here. And this can help you debug other parts of your simulation too, incidentally. Because you're asking for the maximum or minimum, that by definition occurs at one point. Not on a line, it's not on a surface, it's not a volume, it's a point. It has a specific location and only one location in three-dimensional space. So you can ask it not just what is that maximum value, you can ask it for other properties at the same location. That's this co-located fields function. You can say, hey, I want to know where this maximum occurs. Well, we can look at the position in X, Y, and Z. Where does this occur? Well, this is going to occur at probably about 0.3 by a couple of centimeters in the y-axis. Oh, hey, look, the answer is 0.3 meters by 5 centimeters in the y direction. AKA right there. We could also ask it, where's this minimum? We could also ask it, hey, what is the dynamic pressure at that point? Okay, well, we get static pressure still negative 2.88 times 10 to the second. The dynamic pressure at that point is about 551. It's still at the same point, 0.3 by 0.05 meters. So you can ask it for, when you're asking for a maximum or a minimum, you can use this just to measure the values at a point. if we plug in just 1 point, in this case the point on the left here, well, there's only one thing, so the maximum is going to be that one thing. So in this case, it's telling us the value here, right? So if you want to measure the value at a point, you can create a derived part new point probe, and you can ask for a report on the maximum or minimum at that 1 point. Or if you want to create a whole bunch of points and you want to know which one is the highest, you can use maximum or minimum reports. Right? So a lot of these reports are kind of a little bit situational, but some of them are kind of universal. So the big ones that wind up getting used a lot in like aerodynamic contexts are going to be things like mass flow averages, surface averages, mass flow rates, forces, force coefficients, center of loads are big ones in this list. Again, surface average, volume average, maybe. Surface average is a little bit more common. Frontal area, you might if you don't already know it. And maybe, what's the maximum pressure? What's the minimum pressure? Things like that. So some of these are definitely more useful than others. But reports allow you to measure a great many things. And if you don't have a surface where you need to, you can use various derived parts, specifically probes and sections, to measure values where you want. You create a new surface that is derived from the existing geometry in some way. And this will allow you to measure the values where you want. Clearly, these are not the only derived parts. You also have cell surfaces, iso lines, constrained streamlines, vortex cores, blah, 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 etc. Those are also useful in different contexts. The most useful ones in this list are sections and probes, which are taking geometric sections, whether they're planar sections, cylindrical sections, spherical sections. They're constrained or not. I'll get into that later at some point. Or creating probes, which are points. You could create a line. In this case, we just created a line probe, which is 20 points along the surface here. So we can measure like the average on all 20 of these points if we wanted to. Possibly. Let's see here. New. Let's see here. Let's just try. And see if it'll even let us. Oh, it'll let us try and do the surface average on our line probe. Let's do the surface average of static pressure again. Oh, yeah, it has no surface area, so it can't really compute that for this, right? So surface average isn't going to work for that. But you could ask for, what is the maximum value? It's a little bit painfully obvious in this case, but you could ask for what is the maximum value on our line probe, and bonus points, you could ask as a co-located field function, where does that maximum occur? In this case, it's probably going to be this very first one at the inlet, or very close to the inlet, but yeah, it's this very first one, which is 5 centimeters from the inlet, give or take. A little bit less than 5 centimeters from the inlet, but pretty close. Because remember, 0, 0 is over here, so this is probably about 1 centimeter downstream. This is about 6, 11, 16, 21, 26-ish, so negative 25.25. And is a value of 742 pascals at that point. Let me see here. We could also do a presentation grid. which is effectively just an array of points, in this case 20 by 20. Create. You can see we have a whole bunch of points. The other thing that this can be really, really, really useful for is if you're if your eyes gloss over a little bit of this, don't worry too much. But this is relevant to the work I'm currently doing, so I feel like it's worth pointing out. If you want to make sure your simulation's right, kind of the holy grail is doing a test, right? Physically model a thing and then test the exact same thing. So this is really good for what's called model correlation, because you're going to typically measure pressures at discrete points. You can't measure pressure everywhere in a experiment. You can measure pressure in a couple different locations. So what these probes let you do is they let you measure pressure in specific locations. If you measure the pressure in your simulation at the exact same point where you measure your pressure in your experiment, you can directly compare them and do what's called a model correlation. That is, they're not going to agree exactly, but you can tune your model so that it agrees with the experiment. So if you wanted to simulate something else similar, you have greater confidence that it works, because you know it's like, hey, I maybe didn't do an experiment on this exact thing, but we simulated something similar. We did an experiment on something similar, and we got the two to agree for that. So if we simulate this other thing that's close, it should also agree. That's kind of what's called a model correlation effort. If you correlate one model, you have greater confidence in all the others. It's not quite what I do right now, because I deal with satellites in space where there's no air. But one of the big things we do is model correlation. Is we build a thermal model for the satellite. We look at what does that thermal model say about what the satellite's going to do in the test chamber. And then we build a model for what the satellite's going to do in orbit. And then when we run the test, we go back to the model and tweak all the parameters to get it to agree, so that the model of the satellite in the test chamber agrees with what we actually observed on the satellite in the test chamber. And then we take all the same parameters and apply it to simulating the satellite in orbit. So that's kind of a model correlation effort. And you can apply it, in this case, we're not applying it to air in my job currently. But you could apply the same thing to any simulation analysis effort where you do an experimental test. You can do a model correlation effort. And if you have the ability to do that, it gives you much greater confidence in the results. Okay, soapbox over. That was the relevance to my current job. Hopefully that was interesting to a couple people. But in any case, I think that'll do it for today. I've been prattling on for damn near an hour here, and class is only in about 2 hours. So I'm going to wrap it up here and go post this, and you guys can take a look at this later. This is not critical for assignment 1. If you're not taking this class in spring 2023, you can disregard that part. But it's not directly relevant to that. But it might be useful for all kinds of stuff, which is why I'm making it a recording.